Right angle trig. Oh, sorry. This one is stolen from my 3C. So I teach college mathematics. Right angle trig. What is trigonometry?
Triangle and math together.
Sure, yeah. Metric, measurement of. Trigono, triangles. Measuring triangles. Trigonometry is measuring triangles. Makes sense, right? Okay, so, hey, remember Pythagoras? That cool cat, see, finger on the pulse of youth culture, discovered that if you make a square off every side of a right triangle, the two small squares add up to give you the big square exactly. Pretty rad, right? See my use of cool, youthful language? Doesn't this just make you love math that much more? Yeah. So you can see this is old. Anyway, let's get to it. I haven't taught 3C math in a while. And I didn't edit the lesson because I found it charming. So, can I tell you something? I love teaching grade 11 math, and I haven't done it in years. And you guys are like my return too. There you go. See, that's what I'm saying. So, what's Pythagorean theorem? You guys have done this a million times, right? If you had me in grade 9 math, we probably did an activity where we got a bunch of tiles, shut up, and built them off this side of a triangle, right? Did you do this? Did you do it with me? Yeah, and I'll tell you, I don't love the letter version of it. I don't love A, B, and C because then people start obsessing about A, B, and C. To me, it's just like pick a side, make a square. Pick another side, make a square, and then pick the third side and also make a square. And what's going to be true is that that big square is going to be perfectly, absolutely perfectly, the two small squares put together. Now you got to cut up the green square to kind of make it fit. But does that make sense? The big square perfectly equals the two small squares. By the way, this doesn't have to be squares. Do you know that you could put a circle around each of those sides and it would work? You could put a regular hexagon on every side and this would still work. You could put another perfect equilateral triangle on each side and the triangles would add up. Why do we use squares? Because they're mathematically easier. How do you find the area of a circle? Pi r squared. Do we want to do that for all three sides? No. Whereas square, we just do side squared, right? So that's why we use squares. But the truth is, any regular shape off each side would work. So the basic idea then is, yeah, you'll see it given as a squared plus b squared equals c squared, where c is the hypotenuse of a right-angled triangle. What's the hypotenuse? Very good. Longest side, how else can you define it? It's absolutely true. It's opposite to the right angle. Very good. The hypotenuse is the side that is opposite to the right angle, right? So the right angle looks at it. Okay, good. We all remember that. Let's take 2 minutes. Use the Pythagorean theorem to solve for the unknown sides. Again, to me, take the sides you know, make them both into squares, right? Now, do I want you to go get tiles and physically make them into squares? No, that'd be stupid. But rather, we can mathematically make them into squares, which means you would just take, I don't know, let's take this first one. We have one side, and it's 9.0 centimeters. How do I make that into a square? I could just square it, right? What about 14.8 centimeters? How can I turn that into a square? We can square it. Now, in this case, we know that the two small sides always give us the big side. Am I adding these ones together or subtracting? Why am I adding? Sorry? I don't know what that means. Well, sometimes we can. Sometimes we have to subtract. Why am I not subtracting here? I'm trying to find a bigger side. And if I'm trying to find a bigger side, what do I have to do with those two numbers? Add them. Subtracting is not going to give me a bigger number. So do that. And then do the same here. All right? Get these. You're right. So this one's going to be a little different, which is why I say, don't memorize some formula. Do the same thing here. What are the two? So here you said we're going to add these, right? Yeah, by the way, what would we label this side? What would it be called? No A, B's, and C's. This one would be called? Sure, but what's the convention? No, I mean, we could use X. What's the convention? DF or FD, or what's the other convention? Little e, right? The convention, if you haven't learned this before, is angles are done with uppercase letters, and sides are defined by the angle they're across from, and we use lowercase letters. So we could call this side DF, or we could call it side FD, or we could call it side little e. Those are all equivalent expressions to each other. And of course, e squared equals that. So e will equal all of that, 9.0 centimeters squared, plus 14.8 centimeters squared. And what do we have to do with all that if we're going to solve for e? Because this is e squared, right? It's telling us how big this square is. And what do I have to do with that side? Square root it, which how could I express that as an exponent? 1/2. So we're going to do all of that to the exponent 1/2. So go ahead and do that for this one, and then do the same for this one, and come write it down up here. Well, I go boil water to make myself a cup of coffee, and maybe I'll do tea. Yeah, I feel like a cup of tea. Oh my kettle was left in. Kettle was left empty, so there'll be no coffee nor tea for the time. Who earns?
Scarlett, you should go write the question.
I'm not done yet. Okay, I'm sorry. That was really aggressive. I'm not done yet.
I was just trying to be encouraging, Scarlett. I was just trying to.
I don't like writing on there because I feel like I'm scared to write because like what if I forget how to write? You know?
Okay, yeah.
I got it.
But I forget
Hopefully, Carson doesn't forget how to write.
It's an irrational fear. I didn't say it was reasonable. I just said
You are always
Yeah, I know.
Would you quit, Sam?
She has a point. She has a point.
I love how I'm just like picking sides wherever I want. You really just shut up.
I know how to do it.
Hold on, Sam.
That is wrong letter. My fault.
Hey, I got the answer. Wow. So smart. How'd you get it out? Get out of here.
All right, do we have that on my board yet, or what?
Not yet.
Let's go in
What
there.
do we do?
We're being big brain. Did you say someone new?
This is how we do. Right now, we're not doing
The answer is 4.3.
Oh, what did I?
4.3.
I knew that. Listen, I'm nervous right now.
Okay. If you study physics, or if you study computer programming, or if you study, just about anything, boy, do triangles come up a ton. But Pythagorean theorem comes up a billion times. It's just endless how often we use it in settings. Especially, I mean, have any of you taken physics yet? Anyone in physics isn't running right now, is it?
No, next semester.
Next semester.
Oh, I meant to write I, not H.
Do we just give up on units?
Oh. Okay.
Because let's look here. Like this would be 9 squared, which is 81, and centimeters squared would be centimeters squared, and this would be whatever 14.8 is squared, and centimeters squared would be centimeters squared. So we're adding two things with like terms. So this number would be centimeters squared, and then we're taking the square root of it. So we take the square root of the number, yielding 17.3, and the square root of centimeters squared is centimeters. Think in units. Don't just be a math guy. Math people always just do the question, then tack the units on the end. Science people don't do that. And I know this is a math class, not science class, but okay, well this one, it's too late. We'll do that all times centimeters.
Yeah, wrong letter, Mr. Orlando.
Yeah, Mr. Orlando, why would you write it?
Because I'm an idiot. No. Listen, guys, if you're my volleyball team, I'd make you all do push-ups right now. Because we're a team, right? And as a team, we succeed together and we fail together. When one of us gets a question wrong, we all got the question wrong. One of us gets a question right, we all got the question right. No, I'm part of the team too. Also, Also, listen, also, I'm the leader of the team. And let me tell you something else. When you're in leadership, if you're not a douchebag, every failure is your fault. And that's my firm belief. When I was a manager at a restaurant, don't get me wrong, I would follow up with people who made mistakes. But in the end, anything that went wrong on a shift, you know whose fault it was? Mine. Because it's my job to make sure every shift runs perfect. So when something goes wrong, that's on me. Again, someone under you may make a mistake, but your job is to make sure the people under you don't make a mistake. So if they did, is it their fault? Sure, I guess. But even more so, it's your fault. That's what leadership is. It's not about bossing people around making decisions. It's about taking responsibility. And most of the time, that means letting people be free to do what they do, because mostly people are really good at their jobs, and if you just let them do their job, they're going to get it. But sometimes it means stepping in that. Likewise, as a teacher, mostly it means letting you guys figure things out for yourself. And sometimes I actually have to get up here and talk and explain stuff. And then, obviously, I have to rule you with an iron fist, which I do. Now, let's remember how we normally label the sides of a right angle triangle. So there's two elements to this. The first is that if we label this Q, X, and N, doesn't matter, by convention, vertices, and therefore angles, get uppercase letters. Right? And then the follow-up to that is that we would call this side N, we would call this side X, and we would call this side Q. All right? Sides get either named by the vertices they connect, right? So this could also be understood to be QX. This could also be understood to be NX. And this could also be understood to be QN. Or the vertex of which they are opposite. Now, of course, we also name them relative to an angle of interest. We can also name sides relative to any of the angles, and we're going to call that theta. So if we choose one side to be theta, for example, here we are saying let angle X equal theta, then how would we name these? And this you would have learned last year. It says here something new because in my grade 11 review lesson, I steal it from my grade 10 lesson. It's all a lot of thievery, right? If that's theta, what would we call this side over here? What would we call this side over here? If that is theta, that's the angle we're looking at. What do we call the side across from the angle we're looking at when we do trigonometry? The opposite side. Very good. I guess I should write it in full at least once. So if we're looking at side X here, if we're talking about angle X, then side X is the opposite side. If we're talking about angle X as theta, what would we call side Q here? The adjacent. Very good. Adjacent is a word that just means what? Beside, next to, touching. Yeah, good. And this side is also adjacent, so why don't we call it the adjacent? There's two sides adjacent to theta. One of them we call the adjacent, and the other we call the hypotenuse. And hypotenuse is the angle, as we said previously, that is across from the right angle, across from the 90 degree. That should all feel comfortable, right? Yeah. Any of the angles, or let's just say any angle theta. There we go. There we go, that's better. So, this is stupid, but let's just keep it simple. Take 2 seconds, relative to the theta in each case, label the sides of this triangle. All right? Relative to theta, label the sides. When you got it, come right up here. This should be, does this feel like good, comfortable review? I'm not going too fast because we all remember this. If I am going too fast, you put your hand up and say, "Hey, Orlando, you're going too fast." Don't be shy. You can write short forms, yeah. Yeah, that is probably the last time I will ever write opposite, hypotenuse, and adjacent.
Thanks, Scarlett.
No, okay. Not drag Celine Dion like that.
Yeah, don't drink me.
What? He's gone.
You're gonna die.
I look it up like that.
Uh-huh.
Hypothesis was something you could see.
Okay, honestly.
Remember, this was the unit that Alpha taught you like mid-exam.
Oh, yeah. That was so
That was the
He's such a goat for that. Alright, it's like two main groups. There's just normals and wannabe normals.
All right, what do we got? Nice, looks good. How do we feel? No, you don't. Okay, so now, listen. When I teach grade 10, and I don't know how your teacher taught grade 10, but when I teach grade 10, I don't let you ever use a calculator for the like for sine, cos, or tan. I give you a chart. I make you look it up in a chart. And I'm not going to do that with you in grade 11 because you're big boys and girls now. But I wish, if your grade 10 teacher didn't do that, I wish they had. Because I think it really helps us understand, like, before we do this, when we say an angle, what do we mean? Like, if I say, and like it labels it here, so we can actually say the exact number. What is this angle? 32 relative to what? Because you need two lines to have an angle, all relative to 0, right? So when we say that is 32 degrees, what does that mean? Well, the space in between them is always changing. Here it's really close, there it's quite big. Yep. Okay, just at the vertex? The angle at the vertex is a dot.
Oh, wait, no, like...
What's an angle? Okay, but what is an angle, and what does it mean for an angle to be 32 degrees? So let's start with what's an angle. Because here's the thing. I bet if I just threw a bunch of these questions out at you, you do the math and figure out the angles. But here I am asking you a more fundamental question. What's an angle? And we're getting some quick hits. We're getting some tumbleweed. Okay, I like this. Say it again. Yep. Okay, good. So different lines have different slopes, different pitches, which means, right, that a line can lie perfectly flat on a plane, or it can lie elevated, which means that as it moves forward, it also moves up, or while it moves forward, it also moves down, right? So lines can have different slopes. And an angle is a measurement of the difference in their slopes. Okay, what's a degree? This is 32 of them. Yeah?
It's the measurement of which we...
Okay, that's very good. It's the measurement by which we measure angles. So if lines can have different slopes, a degree is a measurement of how different those slopes are. And as it gets bigger, the difference is bigger. If there's 0 degrees between them, they have the exact same slope. And if there's 1 degree, they have a mildly different slope, and so on and so forth. What's a degree? Specifically, what's a degree? Why is this 32 of them? Why isn't this 7? No, I'm serious. Like, what? Why? Talk to me.
So, when you're...
You never thought about this?
No.
No, you just do it.
A fundamental thing, like,
Because degrees are really stupid. Degrees are a really stupid way of measuring an angle. But a degree is basically the idea of this. They basically said, okay, if we started here and came all the way around and came back to here, so if we went all the way around, one full revolution, when it comes to angles, that's all the angles you could possibly have, right? All the possible angles will be somewhere between no angle and all the way back around such that you have no angle again. Does that make sense? Well, what shape do we get if we draw that full revolution? We get a circle. So the idea then was to say, okay, how we could define angles is we could draw a circle. And we could say, if we took that circle and cut it into slices, we could call each of those slices a something. We had the word degree. And how many slices did they cut it into? 360. So we cut the circle into 360 tiny little slices, and we call each one of those a degree. That's 1 degree, and it means that it's 1/360th of a full rotation. Now, may I suggest something to you? What an absolutely stupid number to choose. Right? Like, why in God's... Or why not, here's the thought, why not, I don't know, 100? We do everything else with hundreds, right? And tens. Sure, but 360? Do you know why we use 360? Because the Babylonians counted in 16s, and they came up with this first, and we've stuck with it for thousands of years since. It's fundamentally stupid, right? So a degree is just, when we say 45 degrees, we mean, okay, if you cut a complete rotation into 360 parts, go 45 of those. Does that make sense? 90 degrees means if you cut a full rotation into 360 parts, go 90 of those. But that number is totally arbitrary. What does arbitrary mean?
Useless.
No, it's very useful. Can we all agree degrees are very useful?
Yeah.
What does arbitrary mean? Put your hand down. You've already answered wrong once. Quiet. Random. Random assigned. An arbiter is somebody who will hear your case and make a decision. Somebody made the decision, but it's not based on an empirical thing. You know what I mean? Like measurement is based on an empirical thing, but this isn't. So here's what we say. There's other ways to describe an angle. If we define an angle in degrees, it is cut a full rotation into 360 parts and define by the angle by how many of those parts. Right, so a half rotation would be 180 degrees, quarter rotation would be 90 degrees, right? So on and so forth. That's arbitrary. Is that the only way to define it? Well, the other way we can define it is based on lengths. Based on lengths. And that may seem counterintuitive, but does anyone have a carpenter in his life or her life? Anyone have a mom, a dad, an aunt, and uncle who's a carpenter? I guarantee that something they use all the time is a classic, the simplest Pythagorean triplet. What's the right angle triangle that we use over and over and over and over and over again because it's the one with the smallest numbers? All right angle triangles have 90 degrees. What's the smallest side length right angle triangle? No, 1, 2, and 3 doesn't make a right angle triangle. Oh my God, 3, 4, 5. Actually, the 3, 4, 5 right angle triangle, that's like the thing, guys. That's, if you make one side 3, one side 4, one side 5, and you put them together, you will have a right angle triangle, by definition. It's called a Pythagorean triplet. Sorry? You're washed up. So listen, this is the classic. Do you know how, if you're a carpenter, my dad's carpenter, he builds homes. Does he take a protractor with him to make sure the walls are 90 degrees? How does he make sure the walls are 90 degrees? Yeah, what he does is he frames this wall, right? And you attach that wall, and then you take a measuring tape and you mark it at 4 feet. Then the second wall, you haven't yet attached it, right? You haven't yet attached it, but you put a mark on it at 3 feet, and then you get a 2x4 and you cut it to 5 feet, and when it perfectly fits between those, then you know it's at 90 degrees, you tack that down, and now your wall's perfectly 90 degrees. And if it's a really long wall, you'll do it at 8 feet, 6 feet, and you'll cut the 2x4 at 10 feet. Because obviously I'm just doubling the numbers, right? So a 3, 4, 5 triangle is the same as a 6, 8, 10 triangle. Does that make sense? And that is how we measure that angle at 90 degrees. At any point did I measure an angle? What did I measure? The side lengths. So it turns out the other way we can define an angle is based on lengths. So, in other words, if we have a flat line here, right, and I'm going to draw this. If we have a flat line here, and we pick some arbitrary length here, and then we pick another arbitrary length here, now if I connect them, I have defined an angle. Does that make sense? If you define two lengths at 90 degrees to each other, and then we connect them, we have made an angle. And this is actually, it's funny, this is usually the one we teach you last, but this is the first one because it's based on a simple principle. There's other ways to square things at 90 degrees. Once you have something that you've made 90 degrees, you can use it as a square, right? You ever used a framing square or anything before? It's just a big heavy piece of metal that's at 90 degrees. You butt things up against it. Now they're at 90 degrees, right? So if we do this, but based on our naming convention, if that is across from theta, what would we call this side? So if we take the side opposite the angle, and we take the side next to the angle, we can use those to define any angle. If I wanted to make a bigger angle, I could make the opposite bigger. If I wanted to make a smaller angle, I could make the opposite smaller, right? I could also make the angle smaller by making the adjacent bigger, right? If I keep the opposite the same, but I make the adjacent longer, the angle gets smaller. So that's a way. So we could define it based on lengths. For example, we could say the length opposite the angle divided by the length adjacent to the angle where those two lengths are at 90 degrees to each other. Does anyone know what we call that one? That one has a name. TOA is not its name. TOA is like a little thing we used to remember it. What is its name? It is the tangent of the angle theta. So the tangent of the angle theta is, but what I can't stress enough is this is just another way of describing an angle. If you say that an angle has a tangent of 1, what are you saying? Well, if you're saying the tangent is 1, you're saying that when you make the angle, the two lines you use to make it are going to be the same as each other, right? Because something divided by itself equals 1. So what's, in our old traditional angles way, how would we have described that? So if I said make an angle with a tangent of 1, you'd say, okay, I'm going to make this, pick a number, 10 feet. Then this also has to be 10 feet, right? What would the angle between them be if these two are the same? Come on now. You know this. No, come on. 45, right? Right? 45 is like half and half, right? If you go halfway up but not all the way up, you get 45, right? So these two things mean the same thing. Tangent of 1 is the same thing as saying 45. The difference is tangent of 1 tells you how to build it. Does that make sense? People, I think we teach trig wrong because it sounds like something confusing. Trig isn't confusing. Trig is easier. Every angle in trig is a description of how you build that angle. Does that make sense? If I told you the tangent of an angle is 6, then you know that the opposite has to be how much bigger than the adjacent? 6. So if we went over by 1, that's the adjacent. What would the opposite have to be? 6. And there's our angle. Does that make sense? So could we figure out what that is in degrees? I guess. But here's my point. Why bother? If we had never taught you angles and degrees, and we had taught you angles using tangents instead, it just means, all tangent means is go over this much, then go up that much. It's like slope. It's like the old rise over run slope. Does that make sense? If you look at this, you'll note it is exactly what we used to say in rise over run. The up and downy bit is the top of the fraction, and the lefty righty bit is the bottom of the fraction. But you'll notice we've actually ignored one side of the triangle. And maybe we want to make a description that way. Maybe we want to say, start at a bottom, set your angle, and we want to make that angle by saying, this thing here is 8 feet long, this thing here is 6 feet long. Keep them going until they can be straight on top of each other. Does that make sense? So here I would say use the adjacent side and use the hypotenuse. But that can still be an instruction. Make one 2x4 8 feet long, make another 2x4 6 feet long, and keep changing the angle till they make a 90-degree triangle, and that's what I want your angle to be. What do we call that one? Where I give you the instruction for the adjacent and the instruction for the hypotenuse. Cosine. So the cosine of the angle theta is just saying make an angle where the adjacent side is this long and the hypotenuse is that long. By the way, since they put the adjacent on the top, what will always be true of cosine? What's always the biggest side in a right angle triangle? Hypotenuse. So this number will always have to be, it is cosine, yes. It'll always have to be, you're always going to have a small number over a big number. So what's the biggest this could possibly be? 1. So when you have no angle at all, the cosine would be 1. Does that make sense? Other than that, it's the same. So now listen, if I said a cosine of an angle is 0.5, you'd say, oh, that's easy. The adjacent is 50% as big as the hypotenuse. Does that make sense? So you could get a 2x4, cut it to 6 feet. What would I have to cut the other one to? I'd set that at 6 feet. The cosine tells me that this has to be half as long, so how long would the other one be? 3 feet. And I'd go, oh, those don't meet up yet, so I'd keep angling the 6 foot one, right? Until it's perfectly overhead, and that's the angle. See what I mean? The trigonometric ratios are defining angles by how you would build them. Does that make sense? You think of them as being theoretical math, but actually the trig ratios are construction tools. They tell us how to build angles. And the last one, of course, I did them in opposite order here, is what we call the sine of theta, and that is where, if I told you how long what two sides are. Yeah, I said if you take the opposite side and you divide it by the hypotenuse. I hate that that's always the first one we teach, because it's actually the hardest one to build, right? That's where I give you a hypotenuse, and then I give you the opposite side, and you need to angle them until they make 90 degrees, but it's giving you this angle here. So you're actually changing that angle till this sits flat, but that's the angle we give them. Ironically, sine is the one where you never really use it as a builder because it's really clumsy to build. That's always the first one we teach. In actual, like, day-to-day physics, chemistry, computer programming, all these things, you know what one we use overwhelmingly all the time? Tangent. Because it's the x and the y values. Tangent is just slope, and you're used to doing slope. Does that make sense? Slope is rise over run, right? So when you used to learn that a slope, the slope of this was 3/5, well, actually what you're saying is that the angle was a tangent of 3/5 against there. Does that make sense? If you know the slope of a line, plug the tan inverse into your calculator, and you've got yourself the angle in degrees. What's the stupid nonsense word we use to remember this? SOHCAHTOA. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tan is... Well, listen, I will make you all do push-ups if I ever ask what ratio to use and you say TOA. I'm not kidding. We will all get off from our desks. We'll all do push-ups together. All right? TOA is not a trig ratio. Tangent is a trig ratio. If you want to say tan for short, feel free to do so. You do not tell me that we need to use so, unless you want my pen to be flying at your face 2 seconds later. I'm dead serious about this. I find it so grating. All right? It's like when you go to a restaurant and the server's like, do you want the spin dip? And it's like, I don't need your kitchen short form for things, ma'am. I don't work here. Yes, I would like the spinach dip. I would never say that because I'm unendingly polite to servers, but it does drive me crazy. You ever work at a restaurant, just because you call something by a short form in the kitchen doesn't mean you should talk that way to guests. Anyway, different discussion. Okay, how do we find an angle? Well, finding an angle is trivial. We can use the trig ratios to measure the unknown angle. This theta here, what would the cosine of this theta be? Well, we got to label the triangle. What do we call this side? What do we call this side? What do we call this one? Awesome. So what is the cosine of this angle? Okay, so 4.2 over 18. What is the sine of this? See, I said cosine, and you gave me the sine, but that's okay. I'm just going to change it. What is the cosine? Theta. What's the cosine of this angle? 17.5 over. And what's the tangent of this angle? 4.2 over 17.5. Now, we could express all those as decimals if we wanted to, right? We don't have to, though. I like it as a fraction. Now, if we wanted to know in degrees, what could we do? What about in degrees? Well, if I taught you grade 10, you know what you'd have to do? You'd have to plug that in. Someone give me the sign. We'll do just the one. What's 4.2 divided by 18 in decimals? 0. Give me a couple more. 3 repeating? Okay, so listen. Now, if you were like me when I was in high school, our calculators didn't all have the sine inverse function. We had to go to a sine table. And it was in the back of the textbook, and it was just like 50 pages because it would go to like 4 decimals. And when I teach grade 10, I make people learn it this way because I think there's some valuable in that. But so we would look up and say, okay, if the sine of the angle is 0.233, then we could go and look up sine, and I would look until, and am I going to get it perfectly? No, I'm not. But 2250 is 13 degrees, and 2419 is, so this is somewhere between 13 and 14 degrees. Now you have a button on your calculator where you could say, if sine theta equals 0.233, then we can do something called taking the sine inverse. But I hate this, the way we teach it, because it implies that this is like some kind of mathematical function or some kind of black box. Listen, it's just looking it up in a table. Your calculator doesn't actually have a lookup table. It has an algorithm it uses, but it's basically a lookup table. It's looking it up in a table. It's saying, what is that? Somebody do that? Do the sine inverse of 0.233. And so we get theta being 13 point what? 0.5 degrees? That's fine. There we go. Does that make sense? By the way, could we have used the cos inverse if we wanted to? But again, this is just as much an expression of the angle as that. Saying the angle is 13.5 degrees means take a full circle, cut it into 360 pieces, and go up 13 and a half of them. And if you want to use this, you could get your protractor and build it. But this says, look at me. Shh, look at me. Thank you. This says, if you want to build this angle, cut one piece to 1 meter, cut another one to 0.233 meters, and fit them together at 90 degrees. And you'll get your angle. Does that make sense? And in this case, because it's sine, it's telling you to make the 0.233 one the opposite one, and it's telling you to make the one the hypotenuse, right? And that will give you this angle. Sine of an angle is every bit as legitimate a way to express the angle as the angle in degrees. But if you're going from one to the other, if this sine inverse button is just some black box to you, I hate that. I want you to understand why it works. All it's doing is saying, we know this is a way of describing that angle. And again, I'm going to propose to you it's actually a better way of describing it. It just tells you exactly how to build it, and you don't need a protractor. You need a 90-degree block and a ruler, and you can make your angle. That's pretty cool, right? This, I challenge you without a protractor to make an angle at 13.5 degrees. Do you have any idea how? I wouldn't. I guess I'd try to make a rudimentary protractor by like cutting a circle into fourths, then again into eighths. By the way, will that even get you to 360 nicely? No. Terrible, right? We should have at least used a power of 2 because you could cut something in half over and over again, right? 360 is divisible by 2, but it's not a power of 2. 360 as an angle thing sucks because you can't even build a protractor easily, right? If an angle was measured in 2/56, that would be cut it in half, right? Then cut it in half again. Now you have 4 parts. Then cut those in half. Now you have 8. Cut those in half. You have 16. You could keep doing that to 2/56, and you would have a really nice way of measuring angles because you could make a protractor by getting a piece of paper and just folding it at the same spot, right? But does this let us do that? No. Hate it. But that's okay. Does that make sense? Could I have used the cosine? Sure. The short version of that is this. We'll do one more together. If I want this angle theta, in this particular triangle, let's label the sides. This would be the opposite. This would be adjacent. And this one would be hypotenuse. If we want the angle in degrees, we could just do this. We could say, I'm going to take the sine inverse of, and then what's the sine ratio? Sine is always what over what? Opposite over hypotenuse. So what's the opposite here? 14.1. And what's the hypotenuse? 16.7. Or I could say, let's take the cos inverse of, and what are the angles here? What makes up cos? What over what? Adjacent over hypotenuse. So what number? 9.0 over 16.7. Great. Or I could say theta equals the tan inverse, right? Look up the tangent, and the tangent will be what over what? Yep, so 14.1 over 9.0. I want you to do all 3 of those in your calculator. They should all give you the same answer. It might vary by 1 decimal place somewhere because we're rounding, but it should basically give you the exact same answer. And this isn't a crazy big or small answer, so it should all be the same. But try all 3. And by the way, you need to make sure for the duration of this that your calculator is in what mode? Degrees. Make sure you look at the top and that says degrees. If it doesn't say degrees, it might say rad for radians. And that's a distinct possibility right now because the grade 12 class is working not with degrees right now, but with radians. So you got to make sure it's set up properly. If you don't know how to do that for your calculator, let me know. But can everyone look and see DEG or degrees or D somewhere on your calculator? Not rad? If you see rad, every answer you get will be wrong. Yeah, so yours says radian. So it will not give you a single right answer until we change that. The way you change that is to go down here, scroll, and set it to degrees. Now it says degree. We already found one. Any other yellow calculators say radian at the top? It says radian. Put your hand up. Yes? Over here. Awesome. Press mode. And then down there, over to degree. Oh, up here. Over to degree. Oh, down. Over to degree. Press enter. Now you can just exit. All right, so try those 3. What do we get? Give me just 1 decimal. 57 point what? And this one? 0.4. And this one? 57 point what? And the reason they don't all agree is that this is only 2 digits. And can we use a 2-digit number to accurately get a 3-digit number? No. Does that make sense? So it's just a rounding issue. That's fine. They all agree. Does that make sense? If you know all 3 sides, do I care which one you pick? No. Do you usually know all 3 sides? No. Try this one. And again, for this one, show all 3. And do you see how here I didn't bother 2-stepping it? Like I just said theta equals, and then I just know that since I'm looking for an angle, I'm going to do either the sine inverse or I'm going to do the cos inverse, because inverse means look up the angle in degrees. So why do 2 steps here? You know, let's just, if we're not going to use the table, let's just look it up right away on our calculator. Let's just say I will get the angle by looking up the sine, and the sine is this. I will get the angle by looking up the cos, and the cos is this. I will get the angle by looking up the tan, and the tan is this. Does that make sense? Would you tell me if it didn't? I hate finding sine theta first and then starting a whole new line and saying the sine inverse of sine theta is, because kids start doing crazy things. Crazy things happen where you'll figure out the sine and then take the sine of that. But what we know is we're finding the sine, and so what we need to find is the angle, and sine inverse, the inverse functions. By the way, this is the stupidest nomenclature. You know what this isn't? Very important. What isn't that? It's not an exponent. And that's why I hate this. Do you know what they call these in Britain? Arcsine, arccos, and arctan. That to me is much better because, I mean, even the arc of it I don't love, but at least it makes it clear that it's not an exponent. So important. This is not an exponent. It's just a symbol. All right, you can't square it to make it -2. You can't have that be 1 over sine. You know what I mean? It's not an exponent. It's just a symbol. I hate it. The inverse functions yield angles in degrees. And next year, they'll yield angles in radians for you, but don't worry about that. And again, all the inverse function is actually doing is it's saying, okay, this fraction you gave us, where is it on this table? Does that make sense? Oh, when we work the fraction out at 0.8387, oh, the angle must be 57 degrees. Does that make sense? Like this one, we got 57 degrees. So when you do that, if you do that sine, because it's a little more than 57, its sine is going to be somewhere between 8192 and 8290. I promise, right? If you did the cos, you'd see that it's going to be somewhere between 0.5446 and 5229. If you did the tan, you're going to see it's between those. Does that make sense? All your calculator is doing is looking those up.
I have a question about my question.
Yeah.
It's not an important question.
No, please.
This button's next to those, and it looks like it says hypotenuse. So I'm assuming
It does not say hypotenuse. It is hyper. It is the.
But it has to do with those.
It's related to those, but it is different.
Yeah.
It's. I'm forgetting the name of it. I've studied this. I should know it. I'm embarrassed by myself right now.
I don't even know what it was. I just wanted
Yeah.
to know that it has like the same like.
Now you don't have to do all three of these. Does it ever make sense to find the angle 3 times? No. But I just put all 3 up here to show it doesn't matter. If that's theta, what would we call this side? The way I always remember them is like theta's like a little eyeball looking at the opposite. The 90 degree is like somebody with a really pointy eyeball looking at the hypotenuse. And then the side that's left over is the adjacent. Am I being honest when I tell you that's how I remember it? Yeah, as it happens, I am. Theta, little eyeball looking at the opposite. Okay, so sine it. To find the angle, we could take the sine inverse of the sine. And the sine is what? Opposite is 10.1 over 10.9. If we do the sine inverse of that, what do we get? 67.9 degrees? Yeah, that's fine. Cosine, what would I do? I'd do the cos inverse of 4.2 over 10.9, and that would give me what? Great. And you can see, why are these not matching? Because we only have a 2-digit number here. As soon as we incorporate that 2-digit number, we're going to lose accuracy, right? And tan is going to be 4.2 over... 10.1 over 4.2. I'd pretend I was just testing you, but I wasn't. And what is it? And you can see, in this case, the most trustworthy one, if you want three digits, you should use sine because it gives us 3 digits. Does that make sense? Math teachers don't think that way, but science teachers do. We know that digits matter. Okay, what if we need to find a side? If we need to find a side, we would say this. That we know if that's theta, let theta equal that 33 degree angle, then what do we call each of these sides? What would this be? Well, theta is a little eyeball looking at the opposite. The 90 degree angle is a weird pointy eyeball looking at the hypotenuse. And that leaves us with the adjacent. Okay? So in this case, what side do we know? We know the adjacent, and we are looking for... Okay, so we know A, and we need H. So what angle do we use? Therefore, we should use the cosine, because it equals adjacent divided by hypotenuse. So then we can say, whatever the cosine of 33 degrees is, that's going to equal the adjacent, which is 5.2, divided by the hypotenuse, which is x. As it happens, I can look up the cosine of 33, and if you were in my grade 10 class, that's what we'd do. And we'd say it's 0.8387.
Have a great day, Eagles. Also, there will be no student council meeting today at lunch. No student council meeting today. As well as this is your second last day to get your semi-formal tickets.
How would I solve this for
Come
x?
on down to the front foyer. Thank you.
Yeah, we can multiply both sides by x to get the x out of the bottom, and then we'd have x over here, and then we could divide both sides by... We need to get rid of that, right? So divide both sides. No, just cross-multiplying. God, you guys know how to cross-multiply to solve for ratios? Okay, we'll do a day on that tomorrow. For now, we'll just make it like this. I want to get x out of the bottom, right? So the opposite of dividing by x is multiplying by x. I'm going to do that to both sides. Okay, but at the same time, I don't want x to actually be multiplied by this, so I want to get rid of it. What's the opposite of multiplying by 0.8387? Dividing by 0.8387. Which means I want to multiply this side by x, and then I want to divide it by 0.8387. Does that make sense? The x's will cancel, and what I'm left with is that x will be equal to 5.2, right? Divided by 0.8387, which we can do on our calculator, and it'll give us the answer. 6 point what? Now, to be clear, would I actually turn this into a decimal first? Is there any reason to bother doing that? No, what I would really do is I would say the cos of 33 equals 5.2 over x, and then I know how to cross multiply, so I'd say that's over 1, right? And so I would say cos 33 over times x equals 5.2 times 1, and then I would say therefore x is equal to 5.2 over cos 33. The other thing you can know is that across an equal sign, functionally, you can always swap things from the bottom of one fraction to the top of the fraction on the other side. The reason that works is if I multiply both sides by this, it'll end up here. And if I divide both sides by that, it'll end up down there. Does that make sense? Regardless, we can do that. And then do that in your calculator just to show that there is no point whatsoever in turning this into a decimal first. What's 5.2 divided by cos 33? You're going to get 6.2. Cool? All right, yep.
You lost me a little at the part where, like, you're dividing.
This here?
Yeah,
This is just algebra, all right? There's no new math here. This is just solving for x. When x is on the bottom of a fraction, are we going to solve for it? No, because the best we could ever do is solve for 1 over x. Is that helpful? So do I want x on the bottom of a fraction? So how do I get it out of the bottom of the fraction? Well, the opposite of dividing is multiply. So I multiply that side by x. What happens to my x's? They cancel. But what I do to one side, I've got to do to another. Now, if I wanted to, I could have shown another step here. And I could have said, I could have said 0.8387x equals 5.2. And now to get x by itself, what would I do? I'd divide this by 0.8387. And I'd divide this side by 0.8387. But listen, we've got to get a little bit more confident with our algebra that we're not always showing things in 50 steps, because we're going to get to points where the algebra gets pretty gnarly, and so we've got to have some shortcuts. Does that make sense? Yes. Like the old Swaparoozy, that's just a shortcut, but you got to be comfortable with it. All right? So what do I actually do with these? What I actually do is the old Swaparoozy, where I know I can put the x where the 0.8387 is, and I can put the 0.8387 where the x is, because they're on opposite sides of an equal sign, opposite sides of a fraction. And those algebra skills, don't worry. Am I going to hammer you over the head this unit with some algebra in trig? You're GD right, I am. GD, of course, standing for gosh darn. That's darn with a U. Guys, have a wonderful day. Be kind to one another. Don't marry anyone Scarlett wouldn't marry. No, you can marry Lily. It's cool.
Why my mom like obsessed with you? I don't get it. Like if she had